In 6.2, we're talking about the binomial probability distribution. Think about that word binomial. The prefix bi means two. So in order for us to be dealing with a binomial probability distribution, there are actually 4 requirements that have to be made. Okay, so before you start working a problem and go, oh, that's a binomial, we need to make sure that these 4 criteria are set. Okay, so let me explain what those are. The experiment is performed a fixed number of times. So let me just give you a good example here. Number A, this is a good example of a binomial. An experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 4 free throws, and the number of free throws made is recorded. Okay, this one is a binomial, I'll just tell you. Okay, let's go through these 4 criteria and verify that they're all there. Okay, so number 1, the experiment is performed a fixed number of times or trials. Yes, this is, because they said he's going to shoot 4 free throws. So yes, he shot a specific number of times. We knew ahead of time how many times it was going to be. It was going to be 4. That's a set number of trials. Number 2, the trials must be independent. Yes, independent means that whatever happens on the first one has nothing to do with the other one. So the guy's going to shoot 4 times, and whether he makes the first one or not has nothing to do with whether he makes the second one. They are independent of each other. Okay. Third criteria, the probability of success is the same for each trial. Yes, that works here. And the reason is he historically makes 80% of his free throws. That means every time he goes up to make a shot, he's got an 80% chance of making it. No matter what happened the first one or the second one or the third one, his 4th shot still has an 80% chance of being made. So because each one has the exact same probability, because they're all independent of each other, yes, number 3 is a check. And in the 4th criteria, for each trial, there are 2 disjoint outcomes, success and failure. In other words, they can't both happen. And that's happening here. When he shoots the ball, it either goes in or it doesn't. He either makes it or he misses it. That's success or failure. So yes, this is definitely an example of a binomial. There were a set number of trials. They were all independent. Each trial had the same chance of success. And he either succeeded or failed on each shot. So yes, this is a binomial. Okay. Part B. Let's see if this represents a binomial situation. And by the way, the success or failure is where that binomial term, the 2, comes in. 2 outcomes. You either make it or you miss it. So that's what I call it, binomial. Okay, so scenario B here. A probability experiment in which 3 cards are drawn from a deck without replacement, and the number of aces is recorded. Okay, let's go through our list and see if they work. Remember, we're picking 3 cards without replacement. That means we pick one, we set it to the side. We do not replace it, but we set it to the side. We go back for a second one, we set it to the side, we go back for our third one. And we're recording how many times we get an ace. Okay. All right, so number 1, the experiment is performed a fixed number of times or trials. Yes, that happened. We're drawing 3 cards. It's an exact number. We know how many it's going to be. Number 2, the trials are independent of each other. And that one is where things go wrong here. Okay? Because we did it without replacement. We pick a card, we set it aside, we go back for the next one. Those are not independent of each other. What happens on the first pick will impact the second one because you can't get that same card again. Okay? So because it is without replacement, we are not meeting the criteria for number 2. This is not going to be a binomial. Let's check the other ones just for practice. Third requirement, the probability of success is the same for each trial. That's another failure because whatever we pick the first time, we can't pick that card again because it's going to be sitting on the side. So each card does not have the same chance to be an ace. And in the 4th one, there are 2 outcomes, success or failure. That does happen. We either get an ace or we don't. Okay? But in order to be a binomial, all 4 of these have to be met. They were not all met here, so this one is not a binomial. I'm going to show you in a minute how to do your binomial calculations. But if they ask you to do a calculation for this problem, it would not be a binomial. There might be other ways to do the probabilities, but you will not be using binomial formulas. Okay? All right, part C. According to a recent poll, 28% of Americans state that chocolate is their favorite flavor of ice cream. Suppose a simple random sample of size 10 is obtained, and the number of Americans who choose chocolate as their favorite ice cream flavor is recorded. Okay, so in other words, we go around to 10 people, and we ask them, hey, what's your favorite ice cream? And we want to know whether or not they say chocolate. If they say chocolate, we go, oh, yeah, they said chocolate. If they say something else, we go, oh, okay, they didn't say chocolate. So we're just asking them what their favorite ice cream is. Is it chocolate or something else? Okay. Notice that we believe going into this experiment that 28% of Americans are going to say chocolate is their favorite. So we kind of know about what percent should answer chocolate. Okay. Let's go to our 4 criteria, see if this is a binomial. Number 1, the experiment is performed a fixed number of times. Yes, they told us we're going to survey 10 people, so that one's been met. Number 2, the trials are independent. In other words, when we ask our first person what kind of ice cream they like, does that have anything to do with the second or third person? No, it doesn't have anything to do, so these are totally independent. What one person does is independent of the others. Third one, the probability of success is the same for each trial. Yes, okay. Each one of the people has about a 28% chance of saying chocolate's their favorite, so it's the same for everyone. And number 4, there are 2 disjoint outcomes, success and failure. Yes, they're either going to say chocolate or they're not going to say chocolate. Okay, so that one has been met. This is a binomial. Okay, on your formula chart, it's been a little bit since we looked at our formula chart, but there's a lot of good Chapter 6 information on there. Notice right here on our formula chart, it reminds us that we can do stat calc 1-bar stats L1 and L2 for our expected value. Expected value is the same as mean. That's a reminder from 6.1. Here's a couple of formulas for binomials. We'll get to those in a minute. And then notice that on your chart, I do have listed the 4 requirements to be a binomial. So if you're working a problem and you're going, I wonder if this is a binomial or not, what are those 4 criteria it had to meet? They're listed for you right there so you can try them, okay? And make sure before you actually do start using the binomial formulas. Okay, so a couple of notations we need to be aware of in our binomial formulas. We're going to use capital S to be success. So the probability of success is going to be a P. We're going to use a lowercase p, rather, to represent the probability of success occurring. So up here in the ice cream, the probability of them saying chocolate is 0.28 because 28% of the Americans like chocolate. So we would say that our p-value is 0.28. Okay. F is failure. So the probability of failure is 1 minus. Okay. Yeah, because they're going to be complements of each other. The probability like chocolate is 0.28. Then the probability they do not like chocolate would be 1 minus 0.28, which 1 minus 0.28 would be 0.72. So just keep in mind, P is the probability of success, Q is the probability of failure. Okay. N is going to be the set of how many trials we had. So in this last example with the ice cream, we surveyed 10 people, so our N would have been 10. Okay, and then we let X represent how many successes. And what we mean by that is they're going to ask us questions like, what's the probability that 4 people like chocolate? Or what's the probability that 8 people like chocolate? Or whatever. And so however many they're asking you about, that's going to be your X value. Okay? Now, just know that if they say, hey, what's the probability that 8 people like chocolate? This is the formula for how you find that. Notice that C is our combinations. So, in other words, if we survey 10 people and we want to know the probability that 8 of them like chocolate, it could be the first 8 that like chocolate and not the last 2. It could be the first 3 and then a couple that don't and then 5 more people that do. So there's lots of combinations of where those 8 out of 10 people could fall. So that's why it's got the combination in here. P was the probability of success. So the 0.28 in this case raised up to however many people were involved, in this case 10. I'm sorry, in this case 8 if they ask you for 8 specifically to like it. And then Q would be your probability of failure, so 0.72 raised to the n minus x. This is the formula that you would have to use by hand to calculate the probability that 8 out of the 10 people like chocolate. That's kind of annoying. Our calculator will do it for us. So, but just so you know what the calculator is doing is it's using this formula right here. Okay. In your calculator, we're going to go into a new menu that we have not used previously. In your calculator, you are going to go to the second VARS menu. If you look on your calculator next to the little ring of arrows, there's a button to the bottom left that says VARS. Up above it, it says DISTR. That stands for distribution. To get to anything written in blue, we have to hit the second key. So second VARS, okay, and then there's a long list of choices here, okay? And I'm going to scroll down. Option A says Binomial PDF, and option B says Binomial CDF, okay? Now, you got to make the right choice on when to pick Binomial PDF and when to pick Binomial CDF, but you're going to pick one of those two. Let me tell you the difference between Binomial PDF and Binomial CDF, okay? The PDF stands for probability density function. You will pick Binomial PDF when you're looking for an exact number of successes. If we want to know the probability that exactly 8 out of our 10 people are going to like chocolate ice cream, or we want to know the probability that the basketball player is going to make exactly 2 out of the 4 shots, okay? So if you're looking for an exact number, you'll pick Binomial PDF. The CDF stands for cumulative density function. Cumulative means you're adding them all up. You're going up to a certain number, okay? So if we want to know what's the probability that up to 8 out of our 10 people like chocolate ice cream, we would be picking Binomial CDF. Because up to 8 would include, hey, what if just 6 people like it? Or just 3 people like it? Or exactly 8 people like it, okay? So CDF is cumulative, up to that number, okay? So notice, in either case, Binomial PDF or CDF, you're going to have to know the N number. The N number is your number of trials. You're going to have to know the P number. The P is the probability. So in the case of the chocolate ice cream, the probability that someone liked chocolate was 0.28. So I'll put 10 for my N, 0.28 for my probability, and then X is whatever number you're interested in. Okay, so if we want to know the probability of exactly 8 people liking chocolate, we would put 8 for X. If we want to know the probability that up to 8 people like chocolate, we would use CDF, but we would still be putting 8 for X. Okay, so X is going to be your high number. Notice on your formula chart, it does not tell you the difference between PDF and CDF. You have to know that on your own. But it does remind you for CDF that the X value at the end is your maximum number. Okay, so that does help a little bit. All right, so let's try an example working some problems. According to the Nielsen Company, approximately 30% of U.S. households had a digital video recorder, or a DVR, by the end of 2008. Okay, but it's a lot more than that now. Suppose a simple random sample of 15 households is taken, and the number of households with a DVR is recorded. Okay, and then they ask us several questions about various amounts, like exactly 5 households having a DVR, or at most 4, or more than 3, etc. Okay, all right, so first of all, is this a binomial? Let's go back and look at those 4 criteria and just verify. Remember our 4 criteria. Number 1, there are a fixed number of trials. Do we have a set number? Yes. We're going to ask 15 households. So that is an exact number of trials. In fact, I know that that's going to be my N number. Remember, N is the number of trials. So we're going to go to 15 houses. N is 15. Okay. Next criteria is the trials are independent. In other words, when I go to the first house, does that have anything to do with whether or not the second house has a DVR or not? No, they're completely independent of each other, so we're good. Third trial, the probability of success on a single trial remains constant. Now, they say that approximately 30% of the houses have a DVR, so that means every single house individually has about a 30% chance of having one. So yes, it's the same for each house. And it's P, that's 0.3. The probability of an individual house having a DVR is 0.3. Okay? We don't necessarily need it right now, but just so we know, remember, if P is the probability of success, then Q is the probability of failure. So if there's a 30% chance they do have a DVR, that means there must be a 70% chance, or 0.7, that they do not have a DVR. We don't need to type in Q for right now, but it's nice to know what it is. Okay? All right. And then the fourth criteria, There are only 2 outcomes possible on each trial. Yes, they either have a DVR or they don't. So we're good for all four trials there, or all 4 scenarios, all 4 criteria. Let me say that again. Okay, part A, calculate the probability that exactly 5 households have a DVR. Okay, I like to write the number 0 to 15, and the reason I did that is because I'm going to 15 houses. So when I go to 15 houses, it could be that 0 of them have a DVR, 1, 2, 3, 4, 5, all the way up to 15 could have a DVR. Okay, so how many have them? Somewhere between 0 and 15. I do not know how many there will be until I go and survey them, but somewhere between 0 and 15 of these houses are going to have a DVR. They are asking me to find the probability that 5 of them have it. Exactly 5. Not less than 5, not more than 5, not up to 5, but exactly 5. Okay, since it's an exact number, this is a PDF. So in our we want the probability of exactly 5 having a DVR. Okay? You could have said probability that X equals 5. That would mean the same thing. Okay? All right. On your paper, this is sometimes how the problem will be written. Find the probability of exactly 5 or find the probability of X equals 5. On your paper, I want you to write down how you're going to work it. And you are going to do a binomial PDF. Why is it PDF? Because it's an exact number that we're interested in. Once we pick binomial PDF, it's going to ask us for 3 things. It's going to ask us for the number of trials, which in our case we had 15 trials. Then it's going to ask you for, okay, what's the probability of each one individually having a DVR? Ours was 0.3. And then it's going to want to know, okay, what's the number that you're interested? In our case, it's going to be 5 because that's the number we're interested in. It's exactly 5. Okay, so when you go to binomial PDF, it's going to ask for your N, your P, and your X. Our N was 15, our P was 0.3, our X was 5. And then we'll type this in our calculator. Okay? All right, so remember to get here, we go to second vars, scroll down to binomial PDF. There, oops. Binomial PDF in this case because we had an exact number. It prompts you for the number of trials. We have 15 trials. It prompts you for the P value. In our case, it was 0.3. And for the X value, in our case, it was 5. And I then paste it, and it says that in my calculator. That's what the calculator is going to give me. If you are using an 83, it does not prompt you. It does not say how many trials, what was your P, what was your X. It does not ask you for those. When you hit binomial PDF, it just gives you the parentheses, and you have to know on your own to type 15, comma, 0.3, comma, 5. Okay, so it wants the same thing. You should still make it say this right here. It just doesn't prompt you for those values individually. Okay, and then we hit enter, and it says 0.2061. Okay, here's what that means. That means that there is about the probability of 5 out of these 15 houses having a DVR is 0.2061. Or, as a percent, that'd be 20.61%. There's about a 20.61% chance that 5 out of our 15 houses will have a DVR. Okay? So, I'm going to make this statement here. About I guess if we rounded it to the nearest percent, it'd be 21%. About a 21% chance that 5 out of 15 houses have a DVR. That's how I want to think about that. That's what we just figured out. Okay? Now, my math lab is going to ask it a little different. They are going to say, in 100 trials, in other words, if you went out and surveyed 15 houses, that's one trial. If you went to a second round of 15 houses, that's your second trial. If you went to another 15 houses, that's your third trial. So if you, in 100 trials of 15 houses, in other words, I went to 15 houses, and then another 15 houses, and another 15 houses, and another 15 houses, until I'd done 100 different trials. In 100 trials of 15 houses, 5 have a DVR in how many times? How many of those 100 trials would 5 homes have a DVR? Well, since we did 100 trials, we're going to go to the hundreds place. In this probability right here, the 2 is in the tenths place, and the 0 is in the hundreds place. So if I were to round this to the nearest hundredths place, it would be 0.21. Remember that 6 would send the 0 up to 1. So that's where we got that 21% of the homes have 5 of 15 houses would have a DVR about 21% of the time. So in other words, if we did this 100 times, 5 houses have a DVR in 21 of those trials. So in 100 trials of 15 houses, 5 would have a DVR in 21 of those trials. Okay? If they ask you for 1,000, then you'd be rounding to the thousandths place. So this 1 would not send it up, it would say at 206. So if we did this trial 1,000 times, we would expect 206 of those trials to result in 5 out of 15 homes having a DVR. Okay? All right, part B, calculate the probability that at most 4 houses have a DVR. Okay, well again, anywhere from 0 to 15 could have one. They want the probability that at most 4 have one. Well, at most 4 means 4 is the most it could be. It could be less than 4, but 4 is the most. So I'm going to circle that whole little group right there. Mathematically, we would say x is less than or equal to 4, because we circled all the numbers up to and including 4. Okay? What are we going to type in our calculator? We're going to tell it to do binomial CDF, and the reason it's C is because it's cumulative. It's not just that exact one number of 4, it's all the numbers up to 4. So binomial CDF, it's going to want the N, which is still 15. It's going to want the P, which is 0.3, because each house still has a 30% chance. And then it's going to want our max number. In our case, our max number is 4. All right, so in our calculator, second bars, arrow down to binomial CDF. If you have an 84, it will prompt you for these 3 numbers. If you have an 83, you have to just know that those are the 3 numbers it wants. Paste it into my calculator, and we get 0.515. Let's go 4. Usually my math lab will ask you for 4 decimals, so let's go 0.5155. I like to do 4 decimals because that's usually what my math lab asks for. Okay. All right. So again, that means that we expect for up to 4 homes to have a DVR about 52% of the time. About 52 out of 100 trials, we would have up to 4 homes with a DVR. About 516 out of 1,000 trials would have up to 4 of the 15 homes with a DVR. Okay. Part C is a little different. Calculate the probability that more than 3 households have a DVR. So probability more than 3. Remember, more than 3 means x could be greater than 3. It cannot equal 3. You've got to have more. If 3 homes have a DVR, that's not more than 3. So we're going to say 4 or above. I'm going to circle 4 and up. Okay. Now here's a little bit of an issue. Because it's more than one number, it's not going to be a PDF. So it's going to have to be binom CDF. But the problem is, when we do CDF, we give it our number of trials, we give it our probability, and then we give the max number that we want. When we give the max number assumes we start at 0. It goes, oh, you start at 0 and go up to however high. In this case, we don't want it to start at 0. We want it to start at 4 and go up. So here's what I'm going to do instead. I'm going to calculate this little shaded dotted region, 0 to 3. I'm going to say, hey, what's the probability that it starts at 0 and goes up to 3? And I know that this region, which is not what they asked me to find, And this region, which is what I'm really interested in, this is what they asked me to find, these are complements of each other, which means they have to add up to 1. So if I find this region down here, and I know that this region and this region add up to 1, I could do 1 minus this region, and that would give me this part up here. Okay, so let's type it in this way. 1 minus, second vars, arrow down to CDF, until if there's 15 trials, each one is 0.3, and we're going up to 3. Okay, now notice what happened. 1, that's 100%, minus this little region down here. And if I do 1 minus this region down here, it ought to give me the probability of this region over here that I'm actually interested in. And I get 0.7031. Now if you think about it, I circled the majority of the numbers, 4 through 15. So the probability of being in this region should be pretty high. 70% seems pretty reasonable for that. This region down here must have been just around 30%. If I do second vars, 15, oops, I did PDF on accident, second quit. $15 trials, 0.3 up to 3. That part was just, almost 30%, about 0.2968. So sure enough, 1 minus this little 0.296 left the 0.7 for this region. Okay, so about 70% of the time, more than 3 houses are going to have a DVR. Part D, similar idea. Calculate the probability that at least 10. Probability of at least 10. Well, at least 10 means X is 10 or more. And it's the same idea. We're looking for the high part. Okay, our calculator, when we do CDF, only knows how to find the low part. So I'm going to tell the calculator to do 1 minus the low part. And we can get the low part by binomial CDF, 15.39. The low part went up to 9. 1 minus, second vars, binomial CDF, and I get 0.0037. Okay. Notice that it's very small. Okay, it's a very small chance. Now remember, 30% of the houses have a DVR. So out of 10, what would you expect? What would be your expected value if 30% out of 15 houses have one? Well, 0.3 times 15, we expect 4.5 of the houses to have one. So if we expect 4.5 houses to have one, then the probability of us getting 10, 11, 12, 13, the majority of the houses to have one is low. Okay, so it makes sense that this would be so low because we're only expecting about 4 or 5 houses to have one. Okay, let's try another example here. At the Denver International Airport, 84% of the flights in January 2010 arrived on time. A sample of 12 flights is studied. Calculate the following probabilities. It is a binomial. Okay, each flight has an 84% chance of being on time. There are exact number of trials, 12, so N is 12. Each one has a probability of 0.84, okay, of being on time. Well, so notice how they wrote this here. Probability of exactly 10 are on time. Probability of X equals 10. Since it's a specific number, that's binomial PDF, 12.84, 10. You can type that in. 12.84, 10, and we get 0.2955. So there's about a 30% chance that exactly 10 are going to be on time. Okay. By the way, how many would you expect to be on time? Well, 0.84 times 12, we would expect 10 to be on time, 10.08. That's our expected value. So yeah, that makes sense. For exactly 10, that's 30% of the time there's going to be exactly 10. Okay, sometimes it might be a little higher, a little lower, but it ought to be around 10. All right, part B, at most 9 are on time. So at most 9. 9 is the most. So we're looking for up to 9. So notice X is less than or equal to 9, up to 9. Since this is a multiple number situation, we're going to do binom CDF. Still 12 trials, still 0.84 for each one, and our max number is 9. And we will type that in our calculator. $12, 0.84, and 9. And we get 0.2990. Now look at your rounding for that carefully. This 9 right there, right here, is our fourth decimal, but because the number after it's 5 or higher, that 9 goes up. What's up from 9 is 10, so that carries the 1 over here to the 8, and then puts the 0 in that fourth decimal spot, so 0.2990. That means if we did this trial 100 times, we would expect 30 times out of 100 that there would be up to 9 flights on time. Okay, at least 11 are on time. So at least 11 means 11 or more. So X is greater than or equal to 11. Notice we're looking for the high end. Okay, we don't have a way with PDF or CDF to get the high end. We do have a way to get the low end. So what we're going to do is 1 minus the binom CDF of the low end. The low end has 12 trials. Each one's 0.84, and it goes up to 10. Okay, so this binom up to 10 is the low part. We don't want the low part, so we do 1 minus that thing to get the high part. 1 minus binom CDF, 12.84, we're going up to 10. We get 0.4055 when I round to 4 decimals. Okay, so that's 40% of having the maximum of them arrive on time, which is probably pretty reasonable because out of 12 flights, 1 or 2 are going to have something go wrong and they're going to be late. So a 40% chance of 11 or 12 of them being on time is probably about right. Remember, we expected 10 of them to be on time. So, there was a 30% chance that exactly 10 are on time, 40% chance that 11 or 12 are on time, and then the last 30% was, below 10 that were on time. So that's adding up to about right. Okay, part D, between 8 and 10 inclusive were on time. So we want this right here. We want our X to be sandwiched in between 8 and 10. So 8, 9, or 10 to be on time. Now, a couple ways to do this. Option 1 is to say, well, I know I need to do a CDF. A CDF will start at 0 and go up to the highest end. So what I could do is binom CDF 12.84, 10. That will give me from 0 all the way up to 10. Then I can subtract off the low part that I don't want. I can subtract off the binom CDF of 12.84 to 7. Subtract off the low part I don't want. So binom up to 10 would give me this whole thing. Then subtract off the binom up to 7. And that will work. Okay? So second vars. 12.8410. And then we're going to subtract off second vars CDF up to 7. And that will come out to be 0.5636. 6 when we go to 4 decimal places. Okay? Or, here's option 2, or since it's only 3 numbers that I'm interested, the 8, the 9, the 10, another way I could do it is binom PDF. Remember, PDF is an exact number. 12.848. That will give me the probability of exactly 8. Plus binom PDF 12.849. That will give me the probability of exactly 9. Plus binom PDF of 12.8410. In other words, get the probability of exactly 8, get the probability of exactly 9, get the probability of exactly 10, and add those 3 values together. And you can type it in all at once. So second vars. Sure wish PDF was higher in the list, right? 12.848, so you didn't have to do all the scrolling. Plus second vars PDF of 9 plus second vars PDF of 10. So it's adding all 3 of them up, and notice what we get. We get the exact same 0.5636. So we get the same answer either way. It does not matter which way you do it. You know, some people understand that adding the 3 numbers individually better, and that's fine. It's not so bad when there's only 3. If there had been 7 or 8 numbers, that would have been a hassle. Some people prefer to do find the big circle and subtract off the part you don't want. By the way, I could have PDF'd these 2. I could have just done PDF 11, PDF 12, and added them up. Here I could have PDF'd PDF 0, PDF 1, PDF 2, 3, 4, 5, 8, 9, add them up. It just would take a lot of typing, so I think it's faster to do the CDF. But I just want you to see how those are related to each other. We'll do a separate video for the rest of the 6.2 notes.